Good day everyone, I'm Sureintharaan, matrix number 217012. Today I'll be presenting on fundamental principle of first and second law of thermodynamics for the course of EMM 3226 Thermodynamics 1 by Dr. Nordin. First and foremost, what is thermodynamics? Thermodynamics in physics is a branch that deals with heat, work, and also temperature. And it also talks about the relations to energy, radiation, and also physical properties of matter. Thermodynamics is considered as a microscopic science, which means that it deals with the bulk system and does not deal with molecular constitution of matter. Before we get to know about the law of thermodynamics, it is compulsory for us to know the basic terminologies used in thermodynamics. So firstly, thermodynamic system. There are three systems involved in thermodynamics. The first one will be isolated system, which means that it cannot exchange energy and mass with its surrounding, so the universe is considered an as isolated system. Secondly, open system, where the mass and energy both may be transferred between the system and the surrounding. For example, a steam turbine. Finally, a closed system, where the transfer of energy takes place but the transfer of mass does not take place. For example, refrigerator, compression of gas in the piston cylinder assembly. So the figure beside can show how the system work in thermodynamics. First law of thermodynamics. The first law of thermodynamics relates to heat, internal energy, and work, which is also known as the law of conservation of energy, which states that energy can neither be created nor destroyed, but it can be changed from one form to another form. Let's look at into the explanation of first law of thermodynamics. According to this law, some heat given to the system is used to change the internal energy while the rest is used in doing work by the system. So this law can be represented mathematically in the equation shown here, where delta Q equals to delta U plus W, where delta Q is the heat given or lost, delta U is the change in internal energy, and W is the work done. So the diagram here shows how the first law of thermodynamics works. As we already know the explanation of first law of thermodynamics, it is compulsory for us to know the thermodynamic processes which is also involved in first law of thermodynamics. A system undergoes a thermodynamic process when there is some energetic change within the system that is associated with the changes in pressure, volume, and internal energy. So there are four processes included: adiabatic process, isochronic process, isobaric process, and finally isothermal process. So how does an adiabatic process work? Adiabatic process is a thermodynamic process in which no heat is exchanged between the system and the surrounding. So Q is considered as zero. According to the first law of thermodynamics, Q equals to W plus delta U. So if Q equals to zero, the equation is simplified as delta U equals to negative W. So if work done is negative, internal energy increases and the equation is vice versa. So next is isothermal process. Isothermal process is a thermodynamic process where the temperature remains constant. Internal energy only depends on temperature. So when temperature becomes constant, the internal energy also becomes constant. So according to the first law of thermodynamics, Q equals to W plus delta U. So when delta U is considered as 0, the equation is simplified as Q equals to W. Isobaric process. Isobaric process is a thermodynamic process where the pressure remains constant during the process. So if volume increases, the work done is positive or else negative. So according to the first law of thermodynamics, Q equals to W plus delta U. So the equation for work given as P times delta V. So the equation is expressed as Q equals to P times delta V plus delta U. So when the volume increases, the work done is positive or else negative. Finally, the isochoric process. In isochoric process, the change in volume is considered zero. So a volume change is zero, the work done is also zero. According to the first law of thermodynamics, Q equals to W plus delta U. So when work equals to zero, the equation is expressed as Q equals to delta U. As we already know the terms behind the first law of thermodynamics, let's look at into the second law of thermodynamics. So what does this law says about? So the second law of thermodynamics states that any spontaneously occurring process will always lead to an oscillation in the entropy S of the universe. So entropy is a measure of the disorder of a system where entropy is denoted as using the alphabet S. So in simple words, the law explains that an isolated system's entropy will never decrease over time. The equation for the change in entropy delta S is shown here, where delta S equals to Q over T, where Q is the heat transfer and T is the absolute temperature. For a given physical process, the entropy of the system and the environment will remain constant if the process can be reversed. So the final entropy equals to initial entropy. The process is considered reversible. If the process given is irreversible, the entropy of the system and the environment must increase. So the final entropy must be greater than the initial entropy. There are various statements to explain the second law of thermodynamics. So firstly, Kelvin-Planck statement, which is also known as the heat engine statement. This statement states that it is impossible for a device of heat engine that takes heat from the hot reservoir QH and converts all the energy into useful external work without losing heat to the cold reservoir QC. For the above process to happen, a part of the input engine must be wasted in the environment. In other words, the thermal efficiency of a heat engine cannot be 100%. So the diagram here can explain clearly about the heat engine statement where thermal efficiency of a heat engine cannot be 100%. So the Kelvin-Planck system, from the Kelvin-Planck system, we can derive the equation for thermal efficiency, which is denoted as nth for any engine. So it serves as a dimensional metric for evaluating the performance of a heat engine utilizing thermal energy. So the equation is nth equals to 1 minus QC over QH. So it is important to note that N can achieve 100% efficiency only when there is no waste heat. QC is 0. So based on the diagram shown here, the right part of the diagram can clearly shows that it's impossible to have a heat engine without a waste energy QC equals to 0. Clausius statement. Clausius statement is also known as a refrigerator statement, which says that it is impossible to construct a system that takes heat QC from the cold reservoir at temperature Tc and moves it into the hot reservoir at temperature Th without external work. It is a well established concept of physics that heat moves spontaneously from higher potential to low, and the reverse is not possible without some external work done. So the diagram shown here explain clearly about this Clausius statement. Finally, the Carnot statement. So what does Carnot state in this statement? So the first statement is that thermal efficiency of all reversible heat engines that operate between two thermal reservoirs are equivalent regardless of the type of cycle that each engine goes through. So the second statement is that the thermal efficiency of a reversible heat engine that operates between a hot reservoir and a cold reservoir has a higher thermal efficiency than an irreversible heat engine that operates between the same reservoir. From the Carnot statement, we can derive the mathematical expression for Carnot cycle's maximum efficiency, which is stated below. The equation is nth equals to 1 minus Tc over Th, where nth is the efficiency of Carnot cycle and Tc is the absolute temperature in the unit of Kelvin of the cold reservoir, and Th is the absolute temperature in the unit of Kelvin also of the hot reservoir. Here are simple examples in our daily life which can show how second law of thermodynamics works. In the first picture, we can see that the hot coffee can become cold on its own while it cannot become hot again on its own. In the second picture, we can see that the water flows spontaneously from higher level to lower level, which means that the water cannot flow from lower level to higher level on its own. Finally, Gibbs free energy. So what does Gibbs free energy says? Gibbs free energy is a quantity that is used to measure the maximum amount of work done in a thermodynamic system when the temperature and the pressure are kept constant. So the equation is delta G equals to delta H minus T delta S, where G is Gibbs free energy, H is enthalpy, T is temperature, and S is the entropy. So this table shows how Gibbs free energy relates to second law of thermodynamics. So when enthalpy is less than 0 and entropy is more than 0, the process is spontaneous at all temperature. When the enthalpy is less than 0 and the entropy is also less than 0, the process is spontaneous at low temperature. When the enthalpy is more than 0 and the entropy is also more than 0, the process is spontaneous and only at high temperature. When the enthalpy is more than 0 and the entropy is less than 0, The process is not spontaneous at any temperature, where the process needs energy to continue. Thank you everyone for watching. I hope that now everyone has a basic knowledge of what first and second law of thermodynamics talks about. Thank you.